Okay, so I want to discuss this theorem in a little bit of detail because it's a theorem that sounds like that it'd be an obvious statement on the surface, but it's actually a really useful theorem. The implication is actually really helpful. So let's see. Every absolutely convergent series is convergent. Okay, but what that means is that so if a series is absolutely convergent, that means that this series, if we take the absolute value of every term, when that series converges, then the original series without taking the absolute value must also converge. That's another way of stating this theorem. The usefulness here is that if you've got a series where some of the terms are negative and you wish they weren't, which is actually often the case, because if you recall, so like integral tests, direct comparison tests, limit comparison tests, all of those tests have the requirement that every term in the series is positive, which is often not the case. This theorem says, okay, well, if we suspect that the series we're looking at converges, we are allowed to take the absolute value. If we can show that that series converges, if we say, let me just take the absolute value and make all the terms positive, and I'm going to show you that that series converges, then we can say, okay, well then automatically my series with negative terms in it must also converge. Okay, so that's the usefulness. The proof of this thing I wanted to look at. So let's assume, this is a U. Assume that the series AN is absolutely convergent. I'm going to abbreviate here, absolutely convergent to save myself some room. So that means that the series absolute value of AN converges. Okay, great. Now, note that, let's see, what can we write? AN is less than or equal to absolute value of AN for every positive integer n. I'm going to use this upside down A that means for every, this mathematics notation. So for every positive integer n. Okay. Then this is definitely true, correct? Because absolute value is always positive. So either AN is positive and these guys are equal, or AN is negative and this guy's smaller. Similarly, negative absolute value of AN would be less than or equal to AN, because either this guy's AN is negative and these are equal, because this is always negative, or AN is positive and this is bigger. So this would have to be true for every positive integer n. Okay, so if we add absolute value of AN across the board here, so add absolute value of AN, add absolute value of AN, then we have 0 is less than or equal to AN plus the absolute value of AN less than or equal to 2 times absolute value of AN, right? Okay, for every positive integer n. I want to do that so that I have 0 over here, because now I can apply the direct comparison test. So if this series converges, then that would imply that 2 times that series. So if this is approaching some finite number, then 2 times that series, which would be the series 2 times the absolute value of AN, would also be a convergent series, right? Because we could just bump the 2 out here, and then the series absolute value of AN is convergent, because this is an absolutely convergent series. And I'm just sad that I'm at the bottom of the board. But so by direct comparison test, I can at least fit in this last line here. Direct comparison test, then, if I've got these terms are always smaller or less than or equal to these terms, which are convergent, that puts a ceiling on the partial sums for these guys. So by direct comparison test, this series, AN plus the absolute value of AN, must converge. Okay, so we're maybe a little closer. Now, I'm going to have to erase the top part of my argument here. Hopefully you've got it written down. Note that, let's see, so the series AN would be equal to, so I could write that as AN plus the absolute value of AN minus the absolute value of AN, right? But there's a property of infinite series that says I'm allowed to break that up. So that's equal to the series AN plus absolute value of AN minus the series absolute value of AN. This series we know converges because a series AN is absolutely convergent. So this series right here is approaching some finite number. This series we just proved down here is convergent by using the direct comparison test. So this series here is approaching some other finite number. Well, then the difference between the sums of those two finite series, or the difference between those two convergent series, would have to also be a convergent series. So this series AN converges. There we go. That's what we wanted to prove. So pretty much by direct comparison test, then that series converges with a small adjustment because this isn't necessarily a series of positive terms. But okay, so now you can get away with, or if you suspect your series converges, you can take the absolute value and then apply direct comparison test or limit comparison test if you want to.